All right. So in the previous video, we covered stacks, but in this video, we're going to be taking a closer look at the stack as a data structure and its implementation in C++. So we're going to be looking at how the stack is made, how it's implemented, what functions it provides, and we're mostly going to be looking at it under the hood. So we know that a stack is a data structure where we can push items onto the top and we pop it off the top. And so if we think of this as kind of like a list, this would be the bottom of the list. This would be the beginning of the list. And every single time you add an element to the list, the pointer that points to the top of the list is going to change. So with that in mind, we can actually implement this fairly simply with just having a regular linked list and just having a pointer called top that points to the top element of the linked list. So again, basic functions of a stack. You have an element on the top that you're pushing onto the stack, and when you pop it, so let's say we pop the stack at this current location where it's ABC. When we pop C, the top pointer has to be moved to the next element in the stack. So we're going to be moving the stack backwards. So that in the previous case, before we added C, top was pointing to B, but once we pop it, top will be pointing to B once again, and C will be removed from the linked list. So yeah, this pretty much says what a linked list can do. It's a linear data structure, and that follows a particular order in which the operations are performed. The order is last in, first out. This implies that the element that is inserted last comes out first. And the main things that we want to be doing with this data structure is pushing elements, popping elements, looking at what the top element is, see if it's empty, and know its size. We also want to make some guardrails to make sure that when a stack is empty, we're not just accessing random memory, and we're not. We want to make some guardrails to make sure that if we call pop when it's empty, we're not going to just be messing up and popping an empty list, because that can lead to some nasty errors. And also, if we try to push an element and the stack's already full and we have like a billion items in the stack, we're not going to fry our computer. So yeah, we're gonna have some basic guardrails for that. This just goes over the basics of what this implies. So when we're calling push, we're going to be calling it with a parameter of data. And so when it takes in that data, it's going to be creating a node element and adding that to our linked list, as well as updating the top pointer. So the top pointer is going to be changed after insertion, and it's also going to be changed after pop. So when pop is performed, you're also going to be changing the top pointer. And then this one is just top, just peaks at the top of the stack. So it will tell you, if you run top here, it will tell you that the top is C, but it won't pop it. Pop is when you want to know what elements at the top of the stack without, while also removing it. And the other ones are pretty much self-explanatory, but I'll just leave it here for a second. So by top of the stack, we mean that the newest element. We want to know what the newest element is. So when a new element is added to the stack, it's placed on top of the existing elements. When it's removed from the stack, the topmost element is removed first. And the top of the stack is always the element that is currently accessible for viewing and manipulation. So we can't actually access these underlying elements, the elements at the bottom of the list, until we remove the other elements, until we pop the stack, until it's empty. The pointer through which the elements are accessed, inserted, and deleted in the stack is called the top of the stack. Again, it's a pointer that points to the top of the element. here are some basic applications of a stack. You can use this to add in undo and redo operations. So you can add in the actions that a user commits, and then if you want to undo an action, you just pop the most recent action off the stack, and you can also reverse that by adding that element, that action, back onto the stack. Yeah, so each time an action is performed, it's pushed onto the stack. Undo the action, the top element of the stack is popped. Browser history. Web browsers use stacks to keep track of the web pages you visit. Each time you visit a new web page, the URL is pushed onto the stack, and when you hit the back button, the previous URL is popped from the stack. You can also use it in some data structures and algorithms questions. For example, you can use a stack to check if parentheses are balanced or not. What this means is that if you have a case where if you have a bunch of parentheses and you want to check to see if it's balanced or not, you can use a stack to check to see if each opening brace has an associated curly brace. I won't be going into the implementation of that, but that's what balanced parentheses means, is we're going to be doing that. You can also use it to perform backtracking, and this can be very useful in the case of depth first search. So in some cases, the best scenario is to just try all possible solutions, and you want to be using the stack to implement backtracking, which is you want to try, let's say you have sorry, let's say you have some paths you can take, and you can take like A, B, C, or you can take A, B, D. Backtracking what backtracking means in that case is if once you take the C route, so if you take A, B, C, you can also backtrack and go back to A, B, and potentially take the D route. So it could be go A, B, C, or you can backtrack and go to A, B, and from A, B, you go to D. Yeah. So stacks, the advantage of stacks are that they're really easy to implement. You can, the operations are simple to understand and implement. It's a very efficient utilization of memory. You can have fast access for accessing elements within the stack, as well as removing the elements. This stack can also help for function calls. So like I said, you can have recursive implementation of potential problem-solving strategies. Yeah. So a disadvantage of the stack is that you will have to create guardrails in the case of stack overflows and also stack underflows. So you have to make sure, you have to keep track of the stack size and make sure that your computer can actually hold that much memory. And also that if it's empty, that you're not allowing anybody to just pop from the stack, because then you're popping from a stack that's already empty. And also another big disadvantage is that you can only access the top element. So you can't just randomly access the mid elements from the stack or the bottom elements from the stack. You can only access elements from the top. Yeah, so this makes it really bad for searching algorithms or sorting algorithms. Yeah. And then in the case of if you want to use a stack for recursive function implementation, you can run into some nasty problems where you might run out of memory. To implement a stack using single linked lists, it's pretty simple. You pretty much just have to create a regular linked list with just a pointer to the top. But let's just make sure that it can do the basic operations of popping an element, pushing an element, peeking an element, and displaying the list. So this is what the stack would look like if it was implemented as a singly linked list. You can think of this whole box as the stack, the data structure, and it's going to be comprised of a bunch of linked list nodes. So this one will each linked list node will have data and a pointer, and so the beginning of the stack, the first element of the stack, is going to point to nothing because it's the last element, or rather, it's the first element. And then each previous element, each element on top of that will have data as well as a pointer that points to the previous element, or rather, the next element. So we'll have a bunch of nodes with pointers that point down. And then we'll also have, separately from these linked list nodes, is we'll have a pointer which points to the top. So this top pointer points to the node at the top. And so as you can see here, this is an act of initializing a stack with three elements. So you first add 11, and it's going to have a null pointer. And originally the top pointer would point to 11. When you add 22, it's going to point to 22. And we want to make sure that that node also has a pointer to the next node, which would be 11. When you add another element, a 33, it will have a pointer which points to the next element, which was 22. And so when you add elements, you gotta just make sure that you're first creating this node, you're filling it with the data you created it with, and you're also assigning its pointer, its linking pointer, to the next element in the stack. And then third or fourth, you want to then update the top pointer. So you want to change the top pointer to point to this newly created element. Yeah, so as you can see, the top pointer is moving during this whole time. And when you pop from an element, the top pointer will also be moving again. So if we pop 44, we pop 33, we pop 22, eventually the top pointer will point to 11, and that will be the end of our stack. So yeah, top pointer, that's the most important thing. If I'm repeating it a lot, that's because it's important. That's what makes a stack a stack. A stack contains a top pointer, which is the head of the stack, where pushing and popping items happens at the end of the list. The main advantage of using linked lists or arrays is that it's possible to implement a stack that can shrink or grow as much as needed. Using an array will put a restriction on the maximum capacity of the array, but here each node will be dynamically allocated, so overflow is not possible. Implementing a stack using a singly linked list. Pushing, let's recap on the functions we support. We have push, which is inserting a new element to the stack, which is the beginning of the linked list. Popping returns the top element of the stack, i.e. it deletes the first element from the linked list, and top returns the top element. So this goes on to basically what I mentioned earlier, but we'll go over it again. So when you push an element onto the stack, you first want to create a node. You're going to want to assign the data that you want to assign to that node. So you update the value of that node by data. Node.data is equal to data. And you then link this node to the top of the linked list. So you take the current top pointer and you assign this newly created node's linker, its pointer, to this top of the linked list. And then you also want to update the top pointer to the current node. So to implement a stack using a single linked list, when you pop an element, you first want to check that there's a node present in the linked list or not. If not, then you return early, and this protects us against errors that can mess up our computer. Otherwise, you make a pointer temp to point to the top node, and you move forward the top node by one step, and then you free this temp node. The top operation is to check what the top of the top of the stack is without popping it. So it will check if there's a node present or not. If not, it will return. Otherwise, it will return the value of the top node of the linked list. And so this is what the single stack, singly linked list stack looks like. As you can see, it has a node which has very simple. It's got data and it has a pointer, and this pointer is going to point to the next element in the stack. It's going to point downwards. One second. And so its constructor pretty much takes in data, and it initializes the node's data with that, and it sets the link to null because that will be taken care of by the stack class, which will be wrapping around it and taking care of the actual stack rather than yeah. One moment. And so now we'll be looking at the push function. And so as you can see, it's very simple. You pretty much want to just create a new node with this data. So you'll be initializing this new node with this data that you just created. You want to check if the stack heap is full. This just deals with computer memory, just to make sure that your stack isn't too full and your computer has enough memory to support this operation. This is the case in case you have a stack that's super huge, maybe like 1 billion or 1 trillion items, and your computer can't handle it. So pretty much, if when you called the constructor and you didn't get anything, if you didn't get an item back, you pretty much want to print a Stack Overflow error, and you want to exit out of the program. So that's what this is doing. It's checking if the node you just created doesn't exist. Otherwise, you're going to initialize data into the temp data field. So you're going to grab the node you just made and fill it in with data. And then you're going to want to put the top pointer reference into the temp link. So what this means is you are going to... One moment. Sorry, I had an important phone call. But where are we? So this is pushing an element. So yeah, so this is going to be making sure that this new node that you made, its link pointer. So in the previous slide, we initialized the node and we called its pointer, its next pointer, we called it link. So we are going to change this link to point to the top, the current top of the stack. And then we were going to make this this new node we just made, we're going to make that the top of the stack. So after we make this new node, we make its pointer point to the top of the stack. We then make this this new node the top of the stack. And so I'm going to whiteboard that out. Well, we can imagine this is the bottom of the stack, even though it might be harder to visualize horizontal as opposed to vertical. Let's just consider this to be the end of the stack. And this is what our node will look like. We have a record with data, and this is going to be any data we insert, and a link. And this link will be a pointer. And inside of the stack class, where we're going to be containing all the nodes, we're going to have a single pointer called top. And initially, let's call this D. Let's start filling these in. So instead of having just data, it'll be this one will be D, will be C, B, and A. And so let's say we start the stack off, and initially it's going to be empty. And if we if we push A onto it, this is what the class would look like. So we push A, we call it with A. What it does is it creates a node with A, and then if it's empty, we don't do anything with the link. But once we push this into the stack, we are going to be updating the top pointer. So this top pointer now points to A. When we call it again with B, we'll first be creating the node, and we will be changing this link to point to the top pointer. So we are going to be copying this pointer right here. We're going to be copying it and putting it into our newly created node. So this B is going to be pointing to the same thing. It's going to be pointing to A. And then we're going to be updating this pointer. So this pointer, instead of pointing to A, it'll point to B, because this is the new top of the stack. And then likewise, if we do this again with C, same situation. We create a new node. We change its pointer to point to the top of the stack. And then we update the top pointer to point to the new top, which is the newly created C. If we do this again with D, we're going to have the same case where we update D's link. So D is going to point to the top of the stack, and the top of the stack is going to be C, and we will then update the top pointer. And so that kind of breaks down the push method. The isEmpty function is pretty simple. All we need to do is check the top of the stack, and if top is empty, then we pretty much know that there's no elements. So basically what that kind of looks like is that we don't actually have to know if these elements exist or not. We just have to know if top points to something. So if it points to D, then that means that our stack isn't empty. But as we start to pop elements, and we might get to the case where we delete A even, and we're updating our top pointer. So first would be D, then C, then B. But when we get to A, if we were to delete A, if we were to call isEmpty now, top would be pointing to nothing. So because it points to nothing, we already know that there's no way that there's going to be elements, any elements left in the stack. Because when we do pop elements, we're going to be making sure that we update the top pointer. So if we were to pop just D, whenever we do that, we automatically update the top pointer to point to the next node in the stack. So top just returns the data of top. So whatever top is pointing to, it will return its data. So if it's pointing to C, it's going to return C's data. Yeah, so to pop, all we're going to be doing is we're going to first make sure that we're not popping from an empty list. Otherwise, we're going to be assigning top to temp, and we're going to be assigning a second node to top. So what we're going to be doing essentially is we're going to be creating a temporary variable, and this temporary variable is going to be equal to the top, and we're going to take its link. So we're going to set temporary variable equal to the top node's link. So in this case it's C. We're going to take the link to go to B, and we're going to update the top to point to temp. Let's label this temp. This would be temp. We're going to set it equal to temp. So that would automatically alias to B. And then we're going to call free on this. So we're just going to delete this. And then that's how you pop an element. And then we don't need temporary anymore. But the computer will automatically take care of temp. So yeah, that's it. To display, what we're just going to do is we're going to create a temporary variable that is going to keep, it's going to first print the data of the node, and then it's going to take its link, and then print that data, and then it's going to take its link. And if it ends up into null, if the pointer points to nothing, because if the link pointer, if it doesn't point to any other node, it is by default it points to nothing. If it ever points to nothing, then we know we're at the end of the list, and we don't need to print anymore. So yeah, that is display, and here we have a basic implementation of the stack. So first we're going to be a driver of the program. So first we create a stack, we push elements onto the stack, we display the stack elements, we print the top of the stack, we delete elements of the stack, we display stack elements, we print the top of the stack. Here's some sample code. Oh, I actually didn't put it. Let me insert it real quick. So this is a basic stack class. It's pretty similar to the stack we have. This code, just a few of the variables might be changed. So let's just look at running it. We call stacks, and let's work through the code. So first we initialize it, and we're pushing 10, 20, and 30. And so in that case, when we print the stack, we're going to be printing the top element. So it's going to be 30, 20, and 10. So this is the reverse order of the order in which we pushed it in. And we can see that the top element is going to be 30. If we pop it twice, if we pop the stack twice, first off, we can see it pop. So first we pop 30, and then we pop 20. If you call, if the stack's empty, it's going to say no, because we still got 10. If we push 40 onto it, and then we print the stack, so stack after pushing 40, we get 40, 10. If we print the stack.getSize, we'll get 2. And the benefits of using a stack, of implementing a stack using a linked list, is that you have a dynamic memory allocation. So the size of the stack can increase or decrease dynamically. You're not initializing the stack with a set size in mind. It's going to grow and shrink as needed. This will also give you efficient memory usage. So you only need a next pointer and not a previous pointer. This uses less memory than nodes in a doubly linked list, because in a doubly linked list you have 2 pointers, and here you only have 1. And as you can see, we implemented a stack very easily with just a few lines of code. And you can use stacks to implement other data structures such as queues or linked lists or trees. And that will cover the stack video. In a moment, I will be uploading the queue view video, where we look at the lower level implementation of a queue. But that's as far as it goes for the stack. Thank you very much for watching.